Hello, everyone, and welcome to the virtual planetarium from the Museum of Science. My name is Emily. My pronouns are she and her, and I will be your moderator during this program, which means I am the one watching the Q&A box here in Zoom. So if any of you have questions, if any of you who are watching us in Zoom have questions throughout the program, you're welcome to click on that Q&A box, type in your question and submit it, and I will do my best to relay that question to our main educators today. Also, we do offer live captions during this program, so if you would like to see those captions, you can click on the CC button on your screen and then select Show Subtitles. So with that, I think we can welcome our educators and then we'll get started.
Thanks, Emily. Hi, everybody. My name is Katie. My pronouns are she and her, and today I will be your educator, your main educator, as we talk about the farthest reaches of the universe. But I am not going to be doing it alone.
Hello, everybody. I'm Talia. I also use she, her pronouns, and I'm going to be running the visuals today.
Awesome. So last week, Talia talked about the expansion of the universe. So not only is our universe expanding, but it is getting faster. It's accelerating this expansion. The farther out you get, the faster and faster space is expanding. And so fast, actually, that it's actually expanding faster than the speed of light. Which is a really mind-boggling thing to think about. It doesn't break all the laws of physics because it's the space itself that's expanding rather than like a galaxy moving faster than the speed of light away from us through space. It's the space itself. So it's not technically breaking any laws. But when we think about the expansion, like, is that going to happen forever? Is it going to keep going? Is there a stop to it? Is there an edge of the universe? So that's our topic for today is there an edge to the universe? What is it? How do we define an edge? Because we're going to talk about 3 different types of edges today. So the first one is the edge of what we can actually see. So I'm going to be calling this our truly visible universe, which is bounded by our technology. So basically the farthest that we can see with our technologies. Then the next type of edge we're going to talk about is the observable universe. So this edge is basically everything since the very beginning of the universe, of the Big Bang, everything that has time for the light to actually reach us is considered the observable universe. So theoretically, our current technologies might not be able to see a lot of those objects, but theoretically, we should be able to see them if we had perfect technologies. And then the last edge that we are going to talk about is the actual edge of the entire universe. And I'm going to tell you right now that we don't know the answer to that question. And there are a lot of different possibilities around it. So we're going to talk more about that, but that kind of gives you an idea. So this particular image that Talia is showing us right now is our observable universe mapped out. This is a data set. Our galaxy is right in the middle there. That's the plane of our own Milky Way. So if you've ever gone outside on a very dark night and you've seen the big cloudy band stretching across the sky, that's our own galaxy, which actually blocks out a big chunk of the sky. It's really hard to see through it with telescopes. So that's why a lot of these really massive data sets of the whole observable universe tend to have like a big chunk taken out of them. It's because we can't see through our own galaxy. But everywhere else you can see is a map of all of the galaxies and clusters of galaxies in our universe. And so this is really what we can pick up with telescopes. It's not necessarily the edge of what we theoretically could see. Our technologies need to get more powerful. All right, so to talk about these different edges, we have to understand a little bit more about how light travels through space, and also how old the universe is, because this is all related. So our universe is 13.8 billion years old. That's how far or how long astronomers have measured since the Big Bang using something called the cosmic microwave background radiation. It's basically a map of the very, very early universe. And different techniques can tell us how long ago that radiation was given off. And it's about 13.8 billion years in the past. So that's the time from the Big Bang until present day. Now, over that time, the universe hasn't stayed static. It has been expanding and, again, getting faster and faster as it does. And I mentioned earlier that on many occasions, and for I think the entire history of the universe, it has been expanding faster than the speed of light. So the universe is a lot bigger than just 13 billion light years across, as one might think initially. Now, light, as it travels through the universe, it's the fastest thing, and it travels at a constant speed. So a lot of the times we use light travel time to measure distance in the universe. So a light year, for example, is the distance that light travels in 1 year, and it's roughly 6 trillion miles. So when we start to talk about other galaxies, these numbers get really, really, really big. So using miles and kilometers and things like that, just the numbers get way too big. So we use light years. And on some occasions, you may have heard the term parsec, which is basically like 3¼ light years, but we're going to stick to light years today. So when we're looking out in space at other galaxies, at other galaxy clusters, we're seeing things that are really far away. Like if we're looking at something that's billions of light years away, that means that that light left that galaxy or galaxy cluster 13 or billions of years ago. So we're actually seeing what that galaxy looked like billions of years ago. And over that whole time, the universe has been expanding. So in reality, that object is actually much farther away right now than it is when we look at it, because we're seeing very, very old light. So we'll talk about this a little bit more in just a moment. But the absolute edge of what we are actually able to spot with telescopes is a galaxy called GN Z11. Forgot it for a second there. So this is the absolute farthest object that we've ever seen with the telescope, the Hubble Space Telescope. Specifically, it was part of this Great Observatories Origin Survey, I believe is what it was called. And it surveyed the sky and it looked for the absolute farthest objects that we are able to see, to detect light from. So this particular galaxy is 13.4 billion light years away, and that's in terms of light travel distance. So that's how long it took light to travel. But because of the expansion of the universe, the actual distance, if you were to freeze the universe and get a ruler out and start walking out there, would actually be 32 billion light years away. So as you can see, it's a lot bigger than just like the age of the universe. And the way that scientists can measure these distances is by looking at the spectrum of these objects that are really far away. So this particular galaxy, you'll notice that in its like zoomed in picture there, it appears redder. And that's because as the universe expands, as the space expands, light gets stretched out. So any light that left that galaxy that is traveling through space is going to be stretched out by the fact that the universe is expanding. And so the wavelengths get longer. And this phenomenon is called redshift. And we have like a little animation here that might help you visualize it a bit easier. So we've got the source galaxy on the left, the Earth on the right, and then the light from the galaxy traveling to the Earth, but the space is expanding in between. So that wave gets longer. And maybe we can play it one more time. So it starts off bluer and the waves actually stretch and get longer. So when we look at the light from one of these different distant galaxies, we can actually see this shift and figure out how far away it is based on how stretched out that light is. And so the Z11 part of this particular galaxy's name, the GN-Z11, the 11 means that it has a redshift of 11, which is the highest of any galaxy or galaxy cluster that has ever been measured, which is pretty cool. So this is the edge of what we are able to see with current technologies. And I will stop there and see if there are any questions.
Thank you, Katie. We have had one question come in so far that you actually already answered, but I'd love to ask a related one, which is, has the acceleration of the expanding universe remained constant?
So that's a great question. It has not, or at least we haven't been able to definitively say exactly what that number is. So that number is called the Hubble constant, and it tells us how fast the universe is accelerating, or the acceleration of the universe. And that number ranges, and it actually changes as well. It changed like a few weeks ago. Talia did a show on expansion of the universe. I think it was last week, where she talked about how the Hubble constant has different values depending on how you measure it, and how a very recent measurement came out that was different from the other ones. But they all tend to hover between like 64 to 74 kilometer. Wait, Talia, what are the units again? Something per second per megaparsec?
Yep. It's somewhere between 67 and 74 or 75 kilometers per second per megaparsec, depending on what you use as your measurement object, what kind of object in the universe you're measuring.
Exactly. Right. And just to add really quick, astronomers believe that in the earlier universe, like billions of years ago, the universe wasn't expanding quite as fast as it is now. So it may have changed in the past, but right now it should be relatively constant.
Cool, thank you. Someone just asked, could you break down that unit that you just described for the Hubble constant?
Yeah, so kilometers per second per megaparsec. The kilometers per second is a speed, and it's that speed, kilometers per second, over a megaparsec. A megaparsec is 1 million parsecs. A parsec is about 3.2 light years, I believe. So if we just say it's 3, that means that for every 3 million light years of distance, the universe is expanding by 67 to 74 kilometers per second. So it's gaining that much speed for every megaparsec. And I hope that was clear. It gets very confusing.
Awesome. Thank you so much. I think that's good for now.
Okay, great. All right. So GN-Z11 is the most distant galaxy that we have observed. Light travel time, 13.4 billion light years away. Actual distance, if we could freeze the universe so it wasn't expanding, would be 32 billion light years away. But as I mentioned, telescopes can get better. We can see farther, but there is still a limit to what we can see because of the age of our universe and the speed of light. So this is where our observable universe comes in. So the observable universe is the amount of universe that we could theoretically see because light has had enough time to reach us since the Big Bang. So in this diagram here, we have the Virgo supercluster, which is the supercluster that we are a part of. Our Milky Way galaxy is part of the Virgo supercluster. And we're right at the center of our observable universe. And then from there out, in any direction, it goes about 46 billion light years in all directions. So if you take the entire diameter of the observable universe, it's about 93 billion light years across. So again, we're only at the center because we are doing the observing. So every other galaxy, every other point in the universe has its own observable universe. Some that might overlap with ours, some that might not. And I kind of like to think of it in the same way that we think of social distancing, which I'm sure everybody is very familiar with by now and maybe sick of, but when you're social distancing, you're trying to keep 6 feet from you and the person next to you. So in every direction, right? So you kind of form this 6-foot bubble around you where you're at the center, and every other person has their own bubble where they're at the center. Now, if you think of that as your observable universe, then you are the observer. If you get within 6 feet of somebody, which not recommended during a pandemic, but if you were to get closer than 6 feet with someone, then your bubbles would overlap. So the closest galaxy to the Milky Way is Andromeda, and the closest major galaxy, I should clarify, is Andromeda. And even though it's close, it's still in a different part of the universe. So it has its own observable universe, but most of it does overlap with the Milky Ways, just because the two galaxies are relatively close when you think about the universe as a whole. So the edge of the observable universe is called the particle horizon, because anything that's outside of that horizon is moving away faster than the speed of light. And so light will never actually be able to reach our telescopes. It will never have enough time to actually get all the way, to make that journey all the way to our telescopes from objects that are out there. So we will never, ever, ever be able to see them. And as time continues, more galaxies that are kind of on those outer edges, like the one that we just talked about, Z11, will pass that horizon, and we won't be able to see those galaxies anymore. So given enough time, given a really, really long time, eventually all of the galaxies will be outside of this particle horizon because of the expansion of the universe. So in like trillions and trillions of years from now, the Milky Way, and in 4 billion years, it's going to collide with Andromeda. So it'll be one giant Milkdromeda. So we'll call it Milkdromeda. Will just be one galaxy. And if you were to look out, you wouldn't see anything else. So if there was intelligent life in Milkdromeda in trillions of years from now, they might look up at the sky and think that their collection of stars is the only one that has ever existed. They will have no way of knowing that other galaxies exist because they're too far away. So it kind of makes you think, what could have been pushed out of our visible boundary that we're missing, right? Like billions of years ago, maybe there was a lot more. I mean, there definitely was more within our particle horizon from which we could see that we just will never know exists because we'll never be able to tell with the universe expanding. But this is all topic for next week. Talia is going to go into the future of the universe, and we're talking like the very, very, very far future of the universe. So I'm sure she'll touch more on that. But this particular animation that she is showing us right now This is another data set, an animation of all of the galaxies mapped out in our universe. So it allows you to see the structure and where all the galaxy clusters are located versus clusters that maybe aren't quite as dense, and the filaments that kind of connect the clusters together. And you can see voids in there as well, or the space in between the clusters of galaxies. And that's really the space that's expanding, is in between galaxies and galaxy clusters. Galaxy clusters tend to stay together, and the Milky Way and Andromeda are going to collide because they're gravitationally bound to each other. So expansion of space doesn't have as much of an effect because they're bound by gravity. So anything that's bound by gravity is not affected really by the expansion of space. That's why we're not going to see expansion within our own galaxy or within our solar system or on Earth or anything like that. This is the space in between galaxy clusters. All right. So that's the edge of our observable universe, the particle horizon beyond which we cannot see anything, and we will never be able to see anything. So now we have to figure out what the actual edge of the universe looks like. And in order to do that, or to even begin to contemplate if the universe has an edge, we have to look at the shape of the universe. So when you think of space, you don't really think of it as having a shape because it's everywhere, it's all around us, but we know from general relativity that anything that has mass or energy can warp space. And so a lot of the times astronomers assume that our universe is actually the surface of a four-dimensional shape. It's really hard to imagine 4 dimensions, so we're not going to, try to get into that too much. But basically, astronomers want to know whether or not our universe is curved, because the curvature of the universe will tell us whether or not it goes on forever or if it has an end. And the way to tell if the universe is curved is to measure the amount of stuff that's actually in the universe. So when I say stuff, I mean a combination of mass and energy. So matter, things like stars and galaxies, anything you'd find in a galaxy, like stars and planets and asteroids, all that kind of stuff. That's mass. So is dark matter, which if you tuned in a few weeks ago, you know a little bit about dark matter, but also energy is included because mass and energy are basically the same thing, at least in Einstein's world. So you can measure all of the mass and energy that would be needed for the universe to go on forever. So this is called the critical density. And here we have it written out probably much better than what I just said, the amount of mass and energy that would be needed for the universe, and I have something in the way, to stop expanding after an infinite amount of time. So basically this means that it would be an infinite universe, but this is the maximum amount of stuff that would allow it to be infinite. Because if you have too much stuff, then gravity is going to cause it to just stop expanding and to just pull all the way back. So this is called the critical density, this measurement. Now astronomers can measure all of the stuff in our observable universe. So all the mass, all the energy. And if this amount is greater than the critical density, then that means the universe is going to be curved, because there's so much stuff in it that gravity is going to actually kind of pull it back together. It's going to be closed, so it's not going to go on forever. It will be finite, and it will be shaped kind of like a sphere. So in a sphere, so we think 4D sphere here. We're going to use 3D though, just because it's much more, you can grasp it a little bit easier. So in this particular type of universe, it doesn't have an edge, but eventually if you traveled far enough, you'd end up in the same place. Now, if the measured mass and energy is less than the critical density, the universe is open. It is also curved, but it's shaped more like a Pringle chip. Or a saddle, and it would go on forever. Now, if the energy is equal to the critical density, then the universe is flat, meaning a 4-dimensional plane, and it would go on forever. And that is what current measurements suggest, is that it is flat and on large scales. And so that it probably goes on forever and doesn't have an edge. There are lots of other ideas about the shape of the universe. These are not the only ones. These are just generally the three that astronomers believe are most likely, but it's by no means the only ones out there. And so it's also possible that our observable universe is such a small part of the entire universe that it just looks flat from our perspective, kind of like how on the Earth, when you're just looking around, it looks flat, but we know that it's round from, astronauts going into space and seeing it from a different perspective. So it could be the same thing with our universe. We just don't know. So a lot of unknowns. Any questions?
That was amazing, Katie. Thank you. Yes, I do have a couple that I would like to ask you. One person is still wondering about the speed of galaxies. So in a given second, are all galaxies moving away from each other at the same speed?
They are all moving away from each other, yes. Depending on the distance, they can move away at different speeds. So like the farther we look out into the universe, the faster those galaxies are moving away from us, but we're also moving in the opposite direction from their perspective. So yes.
Okay. And then someone asked, why is gravity more powerful than the expansion of space?
That is a really good question. And that has to do, I think, with the nature of dark energy, which is believed to be the thing that is causing space to accelerate and to expand. And I don't know anything about that really. And also gravity is very powerful when objects are very close to each other. So if, technically everything is exerting a gravitational force on everything else, but it's the distance that says how much that force is. So I imagine that two massive objects that are very close together, that gravity is going to be stronger than the universe expanding. And I don't know why or how.
Awesome. Well, thank you so much, Katie. I think we're officially just about out of time, so we can start wrapping things up. Do you and Talia want to say goodbye to everyone?
Sure. Thanks for joining, everyone.
All right. So folks, thank you as always for all of your amazing questions and participation in these webinars. And we're going over some really crazy stuff this month. So if you would like to see more of our virtual offerings, you can go to mos.org/MOS@home. If you are interested in supporting the museum, you can visit engage.mos.org/welcome. And hopefully we'll see you again next Tuesday in order to talk more about cosmology and all of these amazing things that are going on in the universe. So again, thank you all so much and have a great rest of your day.